Hypothesis testing of the population proportion using a binomial distribution. According to a genetic theory, 45% of plants of a certain species should have red flowers. A random sample of 12 is examined, and 2 have red flowers. We're going to test at the 5% level of significance whether the percentage of plants having red flowers is less than 45%. The critical values method is very good for calculating type 2 errors. But the method is longer compared to the probabilities method. So the sample size n is 12. The test statistic is 2. We're using a 5% significance level. And we're going to test for less than 45%. A one-tailed test. So the null hypothesis, H0, the proportion is 0.45, and H1, the alternative hypothesis, we're testing for a proportion less than 0.45. The random variable x represents the number of plants with red flowers. X follows a binomial distribution. Our sample size is 12, so we have 12 trials, and the probability is 0.45. Because n is 12, then x can take any value from 0 to 12. Some of these values will be in the critical region, and we can use the tables here to calculate which of the values will be in the critical region. 0 to 12. So some of these are in the critical region, and some of these are in the acceptance region. So looking at the probabilities here, any probability that's less than the significance level, or less than or equal to the significance level, it means the x value will be in the critical region. So 0.0008 is below 5%, so 0 is in the critical region, so is 1, so is 2, but not 3. Yeah, this is about 13%, it's more than the significance level. So from here downwards, these values are all in the acceptance region. So we have the rejection region on this side. This is our critical region. We have the acceptance region on this side. The test value is 2, which is clearly in the rejection region. So we will conclude that there is significant evidence that the proportion with red flowers is less than 0.45 or less than 45%. Now the critical value here is 2. Yeah, it defines this boundary here between the rejection and the acceptance region. Yeah, the critical value is 2. So we need to state some evidence why we've selected 2 as the critical value, or why the rejection region ends at 2. So the probability that x is less than or equal to 2, so the probability of the rejection region, is equal to 0.0421. And it's crucial that this probability is less than or equal to the significance level of 5%, so 0.05, which it is. We've rejected H0, which means it's possible that a type 1 error was made, and the probability of a type 1 error is equal to the probability of the reject H0 region, so the probability of this region here, and we have already calculated it, which is this, 0.0421, so this is the probability of making a type 1 error for this context. So the probability of a type 1 error equals the probability of the reject H0 region, 0.0421. The probabilities method is quicker than the critical values method as long as you only want to reach the test conclusion. So you just want to get to a point where you're accepting H0 or rejecting H0. If on the other hand you have to calculate probabilities of errors like the probability of type 1 error, type 2 error, then you need to work out your critical value, the acceptance region, rejection region, and then the critical values method is better. The method starts off pretty much similar to the critical values method. So this is all the same. Now in this example, H1 states we're looking for a decrease in the proportion, and the test value is 2. So we're going to calculate the probability that x is less than or equal to 2. And from the tables, it's 0.0421. So this value is the test statistic, and the less than or equal to comes from here. It's based on H1. And if this probability is less than or equal to the significance level of 5%, then we reject H0, otherwise we accept H0. So as this probability is less than the significance level of 0.05, we reject H0, and here's our conclusion.